Impulse. If a very large force acts on an object for a very short duration, then the force is called impulsive force or impulse. If a force F acts on the object in a very short interval time, let us consider it as a del t. From Newton's second law, we know that the change of momentum with respect to time, that is force. So here we can rewrite the equation F is equal to dp by dt. Instead of that, we can write F dt is equal to dp. By integrating over the time from initial time to final time, that is ti to tf, we will get pf minus pi is equal to integral of ti tf with the force and dt. Here, pi is the initial momentum of the object at time t I, and Pf is the final momentum of the object at time Tf. So, simply we can say that del P is equal to Pf minus Pi, that is change in momentum, and del T is equal to Tf minus Ti during the time interval. So, the integral Ti to Tf f dt is equal to j is called the impulse, and it is equal to change in momentum of the object. That means change in momentum at the particular time, instant time, immediate action for the force, that we can say it as a impulse. If the force is constant over the time, then we can say F del T is equal to del P. So it's called the impulse momentum equation. For a constant force, the impulse is denoted as J is equal to F del T, and it also called change in momentum del P of the object over the time interval del T. Impulse is the vector quantity because it has both direction and magnitude, and its unit is ns. The average force acted on the object over the short interval of time is defined as F average is equal to del P by del T. So here the duration is very short. From this equation, the average force that acts on the object is greater if del T is smaller. Whenever the momentum of the body changes very quickly, the average force becomes larger. So the impulse can also be written in terms of average force. Since del P is change in momentum of the object and is equal to impulse J, we have J is equal to F average del T. So this is the graphical representation of the constant force impulse and variable force impulse. And this is the one example for impulse. The force which act on bodies is for short time are called impulsive. Here the batsman hitting the ball with a bat, or else in driving a nail into a wooden block with the hammer, or in firing a gun, etc. So these are all the examples for impulse. The next topic we are going to see now is friction. It is very gentle force in the horizontal direction is given to an object at rest on the table. It doesn't move. It is because of the opposing force exerted by the surface on the object which resists its motion. This force is called the frictional force, which always opposes the relative motion between an object and the surface where it is applied. If the force is applied is increased, then the object moves after a certain limit. That limit is maintained as a frictional force. The relative motion, when a force parallel to the surface is applied on the object, the force tries to move the object with respect to the surface. The relative motion is opposed by the surface by exerting a frictional force on the object in a directional opposite to the applied force. Frictional force always act on the object parallel to the surface on which the object is placed. There are two kinds of frictions. One is static friction and another one is kinetic friction. Static friction. Static friction is the force which opposes the initiation of motion of an object on the surface. When the object is at rest on the surface, only two forces acting on it. There are downward gravitational force and upward normal force. So this is mentioned as N and this is mg. The resultant of these two forces on the object is 0. So as a result, the object is at rest. If some external force is applied on the object parallel to the surface on which the object is at rest. Now the surface exerts an exactly an equal and opposite force on the object to resist its motion and tries to keep the object at rest. It implies that the external force and the frictional force are exactly equal and opposite. Therefore, no motion parallel to the surface takes place. But if the external force increases, if the external force increased means above a particular limit, the surface cannot provide sufficient opposing frictional force to balance the external force on the object. Then the object starts to slide. This is the maximal static friction that can be exerted by the surface. Experimentally, it is found that magnitude of statical friction forces Fs satisfies the following empirical relations. That is, Fs is greater than or equal to 0 or lesser than or equal to mu s n, where mu s is the coefficient of static friction. It depends on the nature on the surface in contact. N is the normal force exerted by the surface on the body. Sometimes it is equal to mg, but it need not to be equal to mg always. If the object is at rest and no external force is applied on the object, the static friction acting on the object is 0. If the object is rest and there is an external force applied parallel to the surface, then the force of static friction acting on the object is exactly equal to the external force applied on the object. That means Fs is equal to F external. But still, static friction Fs is less than mu s n. When object begins to slide, the static friction Fs acting on the object attains maximum. The static and kinetic friction depend on the normal force acting on the object. If the object is pressed hard on the surface, then the normal force acting on the object will increase. As a consequence, it is more difficult to move the object. The static friction does not depend on the area of contact. That means here we have mass m1 only. So the friction force and the force external force both are equal means that object will not move. If the external force F is increased, then the object will start to slide. It is easier to move because we have only one object, that is m1. But in case that m1 is pressed by the m2, that means the gravitational force and the normal force are increased. Here the n value is m1g plus m2g. So we need more external force to move these two objects. So it's harder to move. Kinetic friction. If the external force acting on the object is greater than maximum static friction, the object begins to slide. When an object slides, the surface exerts a frictional force called kinetic friction Fk. That means the object is in relative motion, it exerts a force, that is kinetic friction. To move an object at constant velocity, we must apply a force which is equal in magnitude and opposite to the direction of friction. That means if you want to stop the object from the relative motion, you have to apply the opposite force that is equal and opposite in direction of the kinetic friction. Experimentally, it was found that the magnitude of the kinetic friction satisfies this relation Fk is equal to mu k n. Fk is the kinetic friction, where mu k is the coefficient of kinetic friction and n is the normal force exerted by the surface on the object. Actually, the coefficient mu k is always lesser than mu s. This implies that starting of a motion is more difficult than maintaining it. That means to push or pull the object at initial, that is static friction, is always greater than the kinetic friction. These are some salient features of static and kinetic friction. Static friction, it opposes the starting of motion. Kinetic friction, it opposes the relative motion of the object with respect to the surface. For example, if you throw a ball, that is static friction, starting. The kinetic friction is try to stop the ball, that is kinetic friction. The static friction is independent of surface area of contact. The kinetic friction is independent of surface area of contact. Now third one, the coefficient mu s depends on the nature of the material in mutual contact. Here it depends on nature of the material and temperature of the surface. It depends on the magnitude of applied force, but kinetic friction is independent of magnitude and applied force. It takes a value from 0 to mu s n. It can never be 0 and always equal to mu k n, whatever be the speed. To move an object, push or pull, which is easier? When a body is pushed an arbitrary angle theta, that is 0 to pi by 2. So this is the angle of pushed force. The applied external force can be resolved into two components. One is F sin theta parallel to the surface and F cos theta perpendicular to the surface. The total downward force acting on the body is mg plus F cos theta. So it implies that normal force acting on a body increases, so there is no acceleration along the vertical direction. The normal force N is equal to N push is equal to mg plus F cos theta. As a result, maximal static friction also increases, so it's equal to mu s mg plus F cos theta. It shows that the greater force need to apply to push the object into motion. Here, when an object is pulled at an angle theta, the applied forces result into two components, that is F cos theta and F sin theta. The total downward force acting on the object is N pull is equal to mg minus F cos theta. So here the normal force is less than N push. So it is easier to pull an object than to push to make it move. Angle of friction is defined as the angle between the normal force N and resultant force R of normal force and maximum frictional force F max. From this diagram, the resultant force R, we can write it as N plus Fs max. The resultant force R, by squaring them in both sides and take the square to the root, so we will get R is equal to root of Fs max square plus N square. To find the angle tan theta is equal to Fs max divided by N. But from the frictional relation, the object begins to slide when Fs max is equal to mu s N, or when Fs max divided by N is equal to mu s. We can write the equation in mu s. From this equation, the Fs max by N is also is equal to mu s and tan theta. So we can equal the equation, that is mu s is equal to tan theta. That means the coefficient of static friction is equal to tangent of the angle of friction. Angle of repose. When an object is placed on the horizontal plane, that object will not slide, but it kept at an angle, the inclined angle, that is we say it as an inclined angle. Now if you keep the object on the plane, the object gets slide. So that particular angle we say it as an angle of repose. For small angle of theta, the object may not slide down. And as theta is increased for a particular value of theta, the object begins to slide down. This value is called angle of repose. Hence, the angle of repose is the angle of inclined plane with the horizontal such that object placed on it begins to slide. The component of the force perpendicular to the inclined plane, we say it as a mg cos theta, is balanced by the normal force N. When the object just begins to move, the static friction attains its maximum value, that is Fs max is equal to mg sin theta and Fs max is equal to mu s N or mu s mg cos theta. By dividing this equation, we will get mu s is equal to sin theta by cos theta. That is sin theta by cos theta, we can write it as a tan theta. So this is equal to angle of friction. Thus, the angle of repose is same as the angle of friction, but the difference is that angle of repose refers to inclined surface and the angle of friction is applicable to any type of surface. Rolling friction. The invention of wheel plays a crucial role in human civilization. One of the important application is suitcases with rolling on coasters. Rolling wheels make it easier than carrying luggage. When an object is moved on a surface, essentially it is sliding on it. But wheels moves on the surface through rolling motion. In rolling motion, when a wheel moves on a surface, the point of contact with surface is always at rest. Since the point of contact is at rest, there is no relative motion between the wheel and the surface. Hence, the friction force is very less. At the same time, if an object moves without a wheel, there is a relative motion between the object and the surface. As a resultant, frictional force is larger. This makes it difficult to move the object. So, ideally, in pure rolling motion of the point of contact with the surface should be at rest, but in practice it is not so. Due to the elastic nature of the surface at the point of contact, there will be some deformation on the contact at the point of the wheel. Due to this deformation, there will be minimum friction between wheel and the surface. It is called rolling friction. In fact, rolling friction is much lesser than the kinetic friction. Dynamics of circular motion. In previous case, we have studied so far only linear motion. Now we are going to study the circular motion. For linear motion, we may need force, external force, or we may not need an external force. But for circular motion, we must need the force to rotate in a circular motion. The velocity of the particle in the circular motion, we can say it in three different ways. One is the magnitude of the velocity can be changed without the changing of the direction of the velocity. The second one is the direction of the motion alone can be changed without changing the magnitude of speed. The third one, both the direction and magnitude of velocity can be changed. That is happen when non-circular motion. In the second case, the direction of motion alone can be changed. That we can say it as a uniform circular motion. We have two types of force in circular motion. One is centripetal force, another one is centrifugal force. Here we are going to see the centripetal force. Consider a uniform circular motion. If the condition for uniform circular motion is the magnitude of the velocity is same at all the time, but the velocity is change in direction. That is the condition for uniform circular motion. That means here the r is the position vector at any point in the circular. The direction of the acceleration is towards the center. So that is the centripetal force. But in any case of the point, the object is released from the circular motion. It goes tangential to the circular rotation. That's why we call it as the direction of the velocity is different at instant time, but the magnitude is same. That is, speed of the velocity is same throughout the circular motion in a centripetal force, that is uniform circular motion. We know that the acceleration of the circular motion A is equal to V square by R. Here V is the velocity and R is the position vector. So here this force is towards the center of the circle. According to Newton's law, the centripetal force is given by FCP is equal to MA. We know that A is equal to V square by R, so that we can write the centripetal force F is equal to MV square by R. The word centripetal means center seeking force. That means the force is seeking the center point of the circular motion. In vector notation, we can write the centripetal force is equal to minus mv square divided by r in the position vector r, because it's seeking the center. So it denotes the opposite direction to the motion. So we mentioned it as a minus mv square by r. In case we have the three types of example here. This is the case of drilling motion of stone to a string. So here also the force is towards the center, and the motion of the satellite around the earth. The centripetal force is given by earth gravitational force on the satellite. So the Newton's second law for satellite motion is F is equal to earth gravitational force is equal to mv square by r. Vehicle on a leveled circular road. When a vehicle travels in a curved path, there must be a centripetal force acting on it. The centripetal force is provided by the frictional force between tire and surface of the road. Consider a vehicle of a mass m moving at a speed v in a circular track of radius r. There are three forces acting on the vehicle when it moves. One is gravitational force mg acting downwards, normal force n acting upwards, frictional force fs acting horizontal inwards along the road. Suppose the road is horizontal, then the normal force and the gravitational force are exactly equal and opposite. So the centripetal force is provided by the force of static friction between the tire and the surface of the road, which acts towards the center of the circular track. So we call it as a Fs is equal to mv square by r. But here we have two conditions, that is the frictional force is lesser than or equal to mu s mg. This is the maximum value from 0. We have two conditions here. If this mv square by r is lesser than or equal to mu s mg, that means the static friction would be able to provide necessary centripetal force to bend the car on the road. So the coefficient of static friction between the tire and the surface of the road determines what maximum speed the cars can travel at a safe turn. But the second condition B, if the mv square by r is greater than mu s mg, if the static friction is not able to provide enough centripetal force to turn, now the vehicle will start to skid. Banking of tracks. In a leveled circular road, skidding mainly depends on the coefficient of static friction mu. The coefficient of static friction depends on the nature of the surface, which has maximum limiting value. To avoid this problem, usually the outer edge of the road is slightly raised compared to the inner edge. This is called banking roads or tracks. This introducing an inclination and the angle is called banking angle. Now let the surface of the road make angle theta with horizontal surface. Then the normal force makes the same angle theta with the vertical. When the car takes a turn, there are two forces acting on the car. Gravitational force mg downward, normal force n perpendicular to surface. We can resolve the normal force into two components. One is n cos theta and another one is n sin theta. The component n cos theta balances the downward gravitational force mg, and component n sin theta will provide the necessary centripetal acceleration by using Newton's second law. That is, n cos theta is equal to mg, n sin theta is equal to mv square by r. By dividing the equation, we get tan theta is equal to v square by rg. Now we can say Vg is equal to root of Rg tan theta. The banking angle theta and radius of curvature of the road or track determines the safe speed of the car at the running. However, if the speed of the vehicle is sufficiently greater than the correct speed, then frictional force cannot stop the car from skidding. Centrifugal force is just opposite to the centripetal force. We know that centripetal force is the force towards the center point. So if you name it as a centripetal force is equal to minus m omega square r, means there is an equal and opposite force that acts on the stone outward with the value plus m omega square r. So the total force acting on the stone in a rotating frame is equal to 0. So the outward force, we named it as a centrifugal force, that is plus m omega square r is called centrifugal force. The centrifugal means flee from center. Note that centrifugal appears to act act on the particle only when we analyze the motion from a rotating frame. With respect to an inertial frame, there is only centripetal force, which is given by the tension in the string. For this reason, centrifugal force is called as a pseudo force. A pseudo force has no origin. It arises due to non-inertial nature of the frame considered. When circular motion problems are solved from a rotating frame of reference, while drawing free body diagram of a particle, the centrifugal force should necessarily be included. Effects of centrifugal force. Although centrifugal force is a pseudo force, its effects are real. When a car takes a turn in a curved road, person inside the car feels an outward force which pushes the person away. This force is also called as centrifugal force. If there is a sufficient friction between the person and the seat, it will prevent the person from moving outwards. When a car is moving in a straight line, suddenly takes a turn, the object not fixed to the car tries to continue in a linear motion due to the inertia of direction. While observing this motion from an inertial frame, it appears as a straight line, but when it is observed from the rotating frame, it appears to move outwards. So this is the example what we have seen. When the person sitting on the seat of the bus or a car, if the car takes the circular rotation suddenly, the person has to move in a straight line. So the force which is pushes outward the center, that is the centrifugal force. A person standing on a rotating platform on a wheels an outward centrifugal force and is likely to be pushed away from the platform. Many a time the frictional force between the platform and a person is not sufficient to overcome outward push. To avoid this, usually the outer edge of the platform is little inclined upward, which exerts a normal force on the person which prevents the person from falling, as illustrated in this figure. Centrifugal force due to rotation of the earth. Even though earth is treated as an inertial frame, it is actually not so. Earth spins about its own axis with an angular velocity omega. Any object on the surface of earth rotational frame experiences a centrifugal force. That's why we are still standing on the earth. The centrifugal force which attracts to the center of the circle, so it appears to act exactly in opposite direction from the axis of rotation. The centrifugal force on a human standing on the surface of the earth is FCF is equal to m omega square r, where r is the perpendicular distance of the man from the axis of rotation by using right angle triangle. The distance r is equal to capital R cos theta, where capital R is the radius of the earth and the theta is the latitude of the earth where the man is standing.